In this video, I will show you a different approach to calculate the output when the input is sinusoidal input. Assume we have a system. Its transfer function is Hs. Let's assume the system is stable. So the input is a cosine function with amplitude A and frequency omega. Then we know in the time domain, the output will be the convolution integral of the input signal. That's the A cosine omega t and the impulse response. It's tau here. So the impulse response, it will be the inverse Laplace transform of the transfer function. The transfer function Hs we know here the integral is from 0 to t. Then we can write the integral as two parts. Here it's from 0 to t. So it can be written as from 0 to infinity, then minus the integral from t to infinity. Therefore, the output yt can be written in this form. The first term, we call it steady state response. The second term, we call it transient response. Why? Because the second term will become 0 when t is very large. This is because when the system is stable, the impulse response will decay to 0 when t is very large. Therefore, the second term is called transient response. Then the first term is steady state response. In the following, I will show you how to calculate the steady state response by using the transfer function. So the steady state response, when the input is a sinusoidal input, then we call the steady state frequency response. Then you know the frequency response of a system is just the steady state response when the input signal is sinusoidal input. Of course, the system must be stable. So we know when the input, for any input, So the output, it contains two parts: steady state response and transient response. Then I will directly show you the result, how to calculate the steady state response. I will not show you the mathematical derivations. So how to calculate the steady state response, that is the frequency response. So the first step, we need to replace the S, the complex number, by imaginary number, Js. The S by J omega. So omega is the frequency of input signal. Then we have Hj omega. Then we know Hj omega, it will be just a complex number if the frequency of input omega is known. Then we can write the complex number in the polar form. We also call it magnitude and phase form. So M will be the magnitude of the complex number evaluated at the input frequency omega. And the phi, we call it phase. That will be the angle of the complex number H evaluate at the input frequency omega. So we know the magnitude, it will be a function of the input signal frequency, and the phase, it is also a function of the frequency of the input signal. Then the steady state output will be the magnitude, the amplitude will be A times M. A is the amplitude of the input signal. Then the ratio M will be the ratio between the output amplitude to the input amplitude. It is exactly the magnitude of the transfer function evaluated at the input frequency omega. Then if the input signal is a cosine function, the steady state output will be a cosine function as well. Then it has the same frequency with the input signal. The only difference is the phase. Then the phase, it can be determined by the transfer function as well. That is the phase of the transfer function evaluated at the input signal frequency. Now you know, if we know the input signal and the transfer function is known, then very easy, we can get the steady state response of the input. The amplitude will be the A times the magnitude of the transfer function evaluated at the input frequency, then plus some phase difference will be the angle of the transfer function evaluated at the input frequency. Now you see, if we have a stable system, if the input is a sinusoidal input, So the output will be also a sinusoidal output. And the amplitude is scaled by the transfer function at a particular frequency of the input signal. And the phase is changed by the phase of the transfer function determined by the frequency of the input signal. Now let's look at an example. We have a transfer function 1 over sk. The input signal is a cosine function. Then we want to determine the frequency response. Then we know the first step. Let's replace S by J omega. Then we have Hj omega will be 1 over J omega plus K. Then we know the output, the steady state response of Yt will be the A times M. M will be the magnitude of this complex number. You see, it is a complex number, just the division of two complex numbers. You can consider 1 as a complex number. So let's calculate the magnitude. Then we know the magnitude will be just this magnitude over this magnitude. So the magnitude of the real number 1, if it's just 1, then the magnitude of the complex number in the denominator will be square root omega square plus k squared. Then the phase, if we draw the complex plane, here's 1. So the phase is 0. Then based on the division will be the phase of this number minus the phase of the complex number in the denominator. So it is, the real part is k, then the imaginary part is omega. So we know the phase is arc tangent omega over k. And now we know the output y as t be just am cosine omega t plus phi. The steady state will be A times M. Once we know the frequency of input signal, then M is just a number, then phi is a number. So here it is the steady state of the output. It is the frequency response. Then we know the amplitude is a function of omega, and the phase is also a function of omega. Sometimes we can plot m omega and phi omega as a function of omega by changing omega from 0 to a very large number. So that's the plot here. So if we take k is 1, So M omega is a function of omega, and phi omega is a function of omega. So when we change omega from here 10 power minus 2, that will be 0.01 until to 100. Then we draw this function, this magnitude function or the phase function. This is called Bode plot. So this is the essential of signal processing. So if you have learned the frequency response in signal processing, then you know that it is just the steady state response. It is not the actual response. It's a steady state response when the time is very large. Now let me give you an example to understand the Bode plot. So that will be the low pass filter. You may learn it in the signal processing class. So let's assume we have an input signal that will be a sine function with frequency 0.1. Then we have this signal, the sine function, is corrupted by high frequency noises. It's shown here. So if I put these two signals together, I put them together, so that will be the sum of these two signals. Now I want this signal here to pass through a system. You see, for this system 1 or S plus 1, it is a stable system. And here it shows the output. Even though the output is not exactly the same with the input, but it recovers most part of the input signal without much of the noises. And how it is possible? So let's go back to the Bode plot. We know the input signal, it has a frequency 0.1. So it will be here. This is the frequency of the input signal. Then we know if this is the frequency, then the output signal, it will be A input amplitude times M, but when omega is 0.1, so the M is very close to 1. So the output amplitude is very close to A. It's very close to the input amplitude. Therefore, you see we have the amplitude 10, and here it's very close. It's 10. Yeah. It's close. It's just a little bit above 10. But if you see the noise, we know here it is a linear system. So linear system, it satisfies superposition. Then what happens when this high frequency noises passes through this system? It has high frequency. If we go back to the Bode plot, if you see here, let's assume the frequency is 100 Okay, maybe it may even be higher than 100. If it's 100, you see the amp, it will be 0.01. Again, you see, let's suppose the noise, let's see, average is 0. I suppose it's pick some values 1. If the input amplitude is 1, then because of the transfer function for this high frequency, the amp will be 0.01. Therefore, for the output, it has an amplitude 0.01. Even though the input signal, it has an amplitude 1. So that's basically the principle of signal processing. So as I told you before, if you understand control, you can understand lots of things.